Talents Valley is pretty unremarkable. It's flat, it's boring in that comforting Northern European way, and it feels like nothing much of any note has ever happened here. But if you were here, crawling through the bushes 3,200 years ago, you'd have come across something a bit like this. Okay, so this isn't Germany, and this isn't 3,200 years ago. There are several ways that you can tell that. First, Bronze Age warriors didn't have cow horns, they didn't have genes, and this is obviously a garden. But we aren't here to talk about my skills at Bronze Age battle reenactment. We're here to talk about metallic bonding, starting with the atom.
I know absolutely nothing about atoms. Obviously I don't. I'm a fearsome Bronze Age warrior, not some sort of spoddy atom nerd. But I also know nothing about lemons. We are where we are. And this lemon is what I'm going to use to explain metal atoms. Now, metal atom, lemon. On the outside, there's a raisin, which I might know about. I might just know that these are tasty. In this case, the raisin is an electron, the outermost electron of the metal atom. Now what's interesting about that is, as with all atoms, it whizzes around, does its thing, but when it meets another metal atom, that's the way that they join. They come together and their outermost electrons get shared. They do something called delocalization. And what you end up with is a soup of metal ions held together in a sea of delocalized electrons. And that is why metals behave the way that they do. It's also the reason why, as a fearsome Bronze Age warrior, I am about to win at the Battle of Talents.
This is the Talents River Valley. 3,200 years ago, 4,000 men met here for a terrible battle, and the river ran red with blood. The first that the modern world learned of that battle was when, in 1996, an amateur archaeologist found an arm bone sticking out of the soil. Today, the evidence of that battle is still being uncovered. There are bones that have been hacked and smashed, skulls with arrows embedded deep inside, the remains of hundreds of men. It was clearly a desperate conflict. Little to nothing is known about it. These people, living on the banks of a small German river, were illiterate. Their heroism is unrecorded, their treachery is lost from history. So we cannot know who was fighting whom or why. But what we can see is that this battle came at a transition point. One arrow, lodged firmly in one arm, is flint. Another, found in a skull, is of a green, tarnished metal. Some bones show the deep gashes of metal swords, yet their owners are holding wooden clubs. Here is where the Stone Age met the Bronze Age, where a new kind of super material was wielded on the European battlefield, and the side that did not master it did not stand a chance. To understand that metal, you have to understand how it's bonded. As a truly fearsome Bronze Age warrior, I obviously have absolutely no idea what a tomato is. But in this case, the tomatoes are representing metal atoms. And what these tomatoes do, as you can see, is they form nice layers. And these layers, because the tomatoes are all basically the same, they slide happily over each other. They go this way and that can be useful if you need something that's slidey. But I don't want my sword to be slidey. I want my sword to be fearsome and hard for a fearsome and hard Bronze Age warrior. So how do I do that? I add a lemon. In goes the lemon. Suddenly, this large lemon stops all of the
tomatoes from sliding over each other. The lemon is normally another metal. And what I've done is I've created an alloy. And from this alloy, I have a super hard tomato and lemon sword.
Let us now leave tomatoes and lemons and talk instead about why there is a thing called the Bronze Age at all. This is, when you think about it, a little strange. Bronze is made of tin and copper, yet we don't talk about tin ages or copper ages. The reason we don't consider these metals worthy of an age goes back to what you saw with the tomatoes and the lemons. And it would have been rapidly apparent to anyone who'd tried to make a sword out of them. Tin is so soft that you can bash it into the shape you want at room temperature. Copper's great advantage today is that it is so soft it can be pulled into wires, useful for internet connections, but less useful for arrowheads. Pure metal of almost any kind is in fact pretty soft, for all the reasons we've discussed. Pure metal is just this ions held together by a soup of negatively charged electrons. And all those free electrons means that metals are brilliant at conducting heat and electricity. But this giant metallic structure with lots of identical ions layered among electrons also has a flaw. It is very easy to slide those layers over each other, which makes it far less effective at, say, shattering an enemy's skull. This is why the invention of bronze was so incredible. When two soft metals, copper and a little bit of tin, came together, they formed something astonishing. They formed a metal that has built empires, vanquished enemies, and changed humanity forever. The tin was like a little bit of grit in the atomic lattice. The different sized atoms stopped the sliding, holding the layers in place, and by stopping the atoms from sliding, alloys make a metal that can be used in tools, in ornaments that survive to this day, and which, on that day, beside the Talents River, produced arrows that didn't stop until they reached the brain.